So in this slide here, you can see examples of good margin and bad margin. So a good margin is a margin in which all sector vectors have the same distance with the maximum margin hyperplane, right? So I will call this as a good margin because uh, all the vectors have same distance or the maximum distance from the maximum margin hyperplane. So we have the hyperplane here, and I can see that this distance and this distance and this distance and this distance is almost the same from the hyperplane itself. So this can be considered as a good margin. On the other hand, the bad margin is the one uh, which can be very close to either class -1 or +1. So if I have two classes here, one is -1 and +1, so the bad margin will be like this one. You can see that these points which belongs to class -1 have a greater margin here, but these data points which belongs to class +1, and they have very minimum margin here from the hyperplane. So these hyperplanes or these margins will be considered as bad, as we don't have a maximum margin hyperplane in this case. So this can be considered as a good margin, and our target is to have a good margin if we want to have a good support vector machine which can classify our input data sets correctly. Another definition is a hard margin or a soft margin. A hard margin, if the training data is linearly separable, right? For example, it means that we can have a line which can exactly classify two different classes. So we can select two parallel hyperplanes that separates the two classes of data. So that distance between them is as large as possible. So in that case, we can have two hyperplanes, and those two hyperplanes can separate those two different sets of data, and we can have the distance between them as large as possible. So that will be considered as a hard margin. On the other hand, the soft margin, as most of the real world data are not fully linearly separable, we know that linearly separable case is very extinct, and in most of the cases it is a non-linear problem. We will allow some margin violation to occur, which is called soft margin classification. So in order to deal with most of the real life situations, we allow the margin to have some violation in that, right? And if we allow some violation, then it will be considered as a soft margin. It is better to have a large margin even though some constraints are violated, right? So this is a very important point. We can have a large margin if we allowed some constraints to be violated, right? Margin violation means choosing a hyperplane which can allow some data points to stay in either incorrect side of hyperplane and between margin and correct side of the hyperplane. So this will be considered as a violation, and it is termed as margin violation, which means that we are choosing a hyperplane, or I am selecting a hyperplane which allows some data to be on the other side of the hyperplane, which will be treated as a misclassification, or those data points will be on the incorrect side of the hyperplane. But just to have the maximum margin, I am allowing this violation, and I am selecting that hyperplane as a hyperplane for the classifier. So let's understand this from this example. So let's see what a hard margin and a soft margin is. Here you can see we have a hard margin, and a hard margin, let's suppose we were very fortunate and we have a linear classification problem, and we obtained this hyperplane, and this hyperplane has a maximum margin from both of the data points from both the classes. So we can treat it as a hard margin, but this is very rare case, and usually doesn't happen in most of the real life scenarios. So in real life scenarios, when we have the data set distribution like this one, so it is possible that some of the data points belonging to this class may be falling from in this category or in this area, because maybe because of some noise or maybe because of some outliers. So now we can draw a soft margin here. Soft margin means that I can select a hyperplane like this one, and this hyperplane has some violations, and that violation is that this data point is basically falling on the other side, right? But since because of this violation, I can have maximum margin for the other data points. So that's why I will allow this violation, and I will tolerate this outlier just because to have a margin which have maximum distance for the remaining data points. So this kind of category will be called as a soft margin. So sometimes, or most of the times, it's better to have a soft margin instead of a hard margin. Okay, now let's go a little bit deeper or in the mathematical side of a support vector machine. So in order to understand the mathematics bit behind support vector machine, we need to revise some concepts of a linear algebra, which you might have studied so many times. So let's look in some terms of a linear algebra, and then we will see that how we can basically represent our support vector machine model mathematically. So if you recall your linear algebra knowledge, you will see that if we have a two-dimensional coordinate x and y, we can expand our two-dimensional coordinate xy into a three-dimensional coordinate system by introducing this z-axis, right? So I can convert my two-dimensional axis to a three-dimensional axis if I have this z dimension here along with x and y direction or x and y axis. The general point P can be represented as 2, 3, 5 and can be represented in the graph as here. So this point P means that it has an x value of 2, y value of 3 and z value of 5. So in a three-dimensional plane here, this point will be lying here having a value of 2, 3, 5, right? Now a vector is denoted by a bold alphabet x. So we can have a vector x denoted by a bold alphabet and we can define its magnitude and the unit vector. So you remember that the magnitude of an n-dimensional vector can be calculated as follows. So if I want to calculate the magnitude of a vector x, it will be represented by these double lines, and I can say that the magnitude of vector x will be under root x1 square plus x2 square up to xn square. So this is a general formula in order to calculate the magnitude of a vector x. Now we also remember from our linear algebra knowledge that this vector x can have a unit vector which is represented by this x hat here, and this unit vector as x hat is a vector which has a length of 1 and it can be calculated by this formula. So remember that the unit vector x hat has a length of 1 and we can calculate it as the vector itself, which is x, divided by the magnitude of vector which we have calculated through this formula, right? So now we know that how can we calculate the magnitude of a vector and the unit vector. So let's remember a few more bits from our previous knowledge. We know that we can represent the equation of a line as y is equals to ax plus b, right? We have used this equation so many times, and we can see that the equation of a line is y is equals to ax plus b. Now if I want to define the equation of a hyperplane, we can define it like this. We can have y is equals to ax plus b, which is the equation of a line, and this equation can also be represented by y minus ax minus b is equals to 0. So if I take this term on the other side of this equation, we will see that it will turn out to be y minus ax minus b is equals to 0. Now I can have two vectors. If I have been given two vectors, then on the basis of this equation, these two vectors can be given as w, and the coefficients of this vector w will be this minus b, this minus a, and since we have 1 here with y, it will be 1, right? And for the vector x, right, it will be 1, which is here, and then we have this x, and we have this y, right? So for these two vectors, w and x, we can have the w transpose of x can be written as, so w transpose of x will become minus b into 1, right? This one, minus b into 1 plus minus a into x, which is this one, plus this 1 into y, which is this one. So my w transpose of x will comes out to be, from this equation, it will become y minus ax minus b, and you will note that this y minus ax is similar to this equation here.